A badly implemented database connection pool turns a traffic spike into a connection storm. Let's see how we can implement a JDBC connection pool in the right way and use a database proxy such as Open J Proxy so that your services scale efficiently without killing your database. A JDBC connection is a stateful session on a database server. It may include things like authentication state, current transaction context, session settings, and temp objects. Creating a connection requires network handshake, authentication, session init, so these are expensive operations that should be kept to a minimum. Connection pool helps to achieve that. A pool keeps a set of pre-established database connections and hands them out to the application threads on demand. So, instead of creating a brand new DB connection for every request, the application borrows one from the pool, uses it, and then returns it. This way, the pool reduces the cost of database connections by reusing them. It also enforces back pressure so that DB is not overloaded. In other words, it is a concurrency gate in front of the very scarce resource, which is the database. But remember that a connection pool is not a performance cheat code. It doesn't make slow queries fast, nor does it make bad SQL good, but it makes contention visible. You can implement your own connection pool or use the established frameworks such as Hikari CP, Apache DB CP, or C3P0. Let's use Hikari CP, a lightweight and very fast JDBC connection pool. It is also used by default in Spring. Creating a connection pool with Hikari CP is pretty straightforward. You create a Hikari config object, pass the URL, user, and password as a minimum, and then you pass this object to the data source. But of course, Hikari offers a lot of properties to configure the pool, such as the maximum pool size, connection timeout, and many others. You can configure them programmatically or in the application properties. And actually, if the pool does your application good or only makes matters worse, depends on how well you configure it. And why is that? You see, applications today are composed of dozens of microservices. They scale independently, deploy independently, and often run in environments where instances appear and disappear constantly. But databases are still stateful, resource-constrained systems. They have hard limits on concurrency, memory, and connection handling. And so, troubles start when highly dynamic applications talk to a bounded database. In most Java applications, each service runs its own connection pool. Kubernetes and similar solutions add instances very fast. So, each instance starts a connection pool and tries to fill it. Every instance asks for connections freely, and the database absorbs this pressure until, well, it can't. As a result, applications can request many connections at once, but databases can service only a limited amount efficiently. The result is connection storms, unpredictable latency, and instability under load. If the latency reaches a certain limit, it all triggers timeouts. A pool timeout, in turn, will trigger the retry logic. Retries increase concurrency, leading to even bigger latency and more timeouts. So, how do we break this vicious circle? Or better, how do we not get into this vicious circle? Well, first, limit the pool size and couple it to the request concurrency. One way of calculating the pool size is this. First, measure real DB time per request. It means take your main endpoints and measure the time necessary for a DB connection, which is the query plus transaction time. Then, use Little's law to estimate required concurrency. Pick a target throughput and multiply it by DB time. For example, the target throughput is 200 operations per second, the DB time is 200 milliseconds, and as a result you get 4 concurrent DB connections required for this workload. Note, however, that you should increase the pool size only until the throughput stops improving, or latency starts rising. This is because oversized pools usually decrease throughput by increasing DB contention. For example, Hikari CP docs explicitly warn against pool oversizing. The second important step is to align timeouts. Timeouts lead to wasted resources, cascading failures, and retry storms. That's why aligning them is important. But how? Every downstream step should have a smaller timeout. So, request timeout that faces the user directly should be bigger than query or statement timeout. Otherwise, the client may give up, but the DB will continue working. The pool acquisition timeout should be the shortest one. Otherwise, the application can queue forever, waiting for a connection. And thirdly, consider using a database proxy. A database proxy sits between the application and the database server, centralizing connection management. Applications can open many logical connections, while the proxy limits the number of physical connections. This reduces connection storms and improves reuse. There are several database proxies on the market. Most proxies like PG Bouncer, Proxy SQL are tied to a single database protocol. Plus, they require external load balancers for higher availability. This adds to operational complexity. But in this video, we'll explore Open J Proxy. It integrates directly with JVM applications and reduces the number of external dependencies. But before going deeper, it's important to clarify the scope of responsibility. OJP does not remove the need for sound schema design and capacity planning. Its primary role is to control the connection pressure, concurrency, and workload behavior at the system level. Open J Proxy, or OJP, consists of two main components. The OJP server runs as a standalone process and acts as a Layer 7 database proxy. It understands SQL-level operations and manages real database connections internally, using technologies like Hikari CP and native JDBC drivers. The OJP JDBC driver is a Type 3 JDBC driver. It does not talk to the database directly. Instead, it communicates with the OJP server over gRPC and protocol buffers. This design gives the application protection from the connection storms and enables it to benefit from circuit breakers and back pressure. And you don't even need to change the application code. From the framework's perspective, it's just another JDBC driver. Also, OJP offers several unique features, such as deferred connection acquisition, slow query segregation, and client-side load balancing. In traditional JDBC, a connection is acquired before the query is ready to execute. It means that database resources are held while the application is still preparing statements or executing some business logic. But OJP changes this behavior. When an application requests a connection, OJP returns a virtual connection handle. No real database connection is acquired yet. Only when the application actually executes a statement, the OJP allocates a real connection from its pool. This change results in fewer idle connections, better use, and higher throughput per physical connection. Applications can be configured with multiple OJP server endpoints. The JDBC driver itself performs intelligent load balancing and failover. So if one OJP server goes down, the driver automatically routes traffic to the remaining nodes. Connections are rebalanced and throughput remains stable. Plus, there is no need for a load balancer in front of the OJP. Removing that layer eliminates the extra network hop, avoids routing inconsistencies for stateful sessions, simplifies the overall architecture, improves latency and reliability. OJP also has a feature called slow query segregation. Instead of letting long-running queries block fast transactional workloads, OJP dynamically detects slow operations at runtime and routes them into separate execution lanes. OJP observes real behavior, labels workloads adaptively, and isolates slow queries automatically. To avoid wasted capacity, OJP also implements the work stealing strategy. If slow query lanes are idle, they can be temporarily borrowed by fast queries, and vice versa. This way, fast queries stay fast, slow queries are isolated, and capacity is never wasted. This behavior is driven by observed runtime characteristics. In upcoming releases, it can be complemented with a structured query analysis to validate and improve queries. The fastest way to start with OJP is to run an OJP server with Docker. Alternatively, you can run it as a standalone jar. Then, add the OJP JDBC driver. Finally, update the database driver class and database URL by prefixing it with the OJP information. And that's it. Run your application as usual, and it will use OJP as a proxy. OJP works with major Java frameworks, so you can configure it in a familiar way. For example, this is how you do it with Spring. Connection pools reduce the database overhead, but they don't make the database faster. They cap concurrency so that your application fails predictably instead of simply dying. To prevent the connection storm and other nasty issues, configure the pool size and align timeouts. Also, consider using a database proxy to increase the database stability. Don't forget to like this video, subscribe to our channel, and until next time!